Okay, we are going to make a simple beam problem using LS Dyna. Our goal is to make some structural problem using LS Dyna and to know how to use this program in our analysis. So our problem that we are going to start to solve is this problem. We have a simple beam. The simple beam consists of span 5 meter length, and the force is concentrated force in the middle is 10,000 Newton, and the beam cross section is as shown here is 0.2 meter by 0.6 meter. So to do this in the LS Dyna, first we are going to make a brief introduction for the tabs here in the window. First we are going to start with these tabs. These are the geometry tabs. Most likely they are used to create a geometry in order to make an element after that. And after using these these tools to create our geometry, we are going to use these tools to create our element from this geometry. After making the element, we are going to make the run and then go to the third tool, which is post-processing. Using this tool we can view our output and print our results. So in our problem we want to draw a line. This line will describe the beam, so we are going here in the geometry tool. We are going to use curve. In the curve we have several tools to draw our beam, so we are going to use only a simple line. Here in the line, when it's shown here, he gave you the start point and the end point. So according to the problem here in the PDF, the start point will be, for example, this point is start in x0, y0, z0, and end at x equal to 5. We are using the coordinate system that the horizontal axis is the x-axis and the vertical axis is the z-axis. So let's go back to our problem. So the start point 0, 0, 0, and the end point will be 5 meter, and y0 and the z equal to 0, 2. When I click apply, it will show you that here's the beam. If you want to show the whole beam, you can click here in the auto center. It will show you the whole beam in the view. Okay, now after creating the geometry, we want to change this geometry to an element, to a beam element. So to do that we are going to use these tools, which can, or especially this tool, it's element and mesh tool, which can help us to convert from this geometry to an element. So we are going here, and then we are going to use this tool, which is element generation. In element generation tool we are going here, and you will find that you can create a beam, a shell, or a solid. In our case we are using to make a simple beam, so here I'm choosing to make a simple beam. The first is the element ID. For any element have been created in the LS Dyna, he gave them a numbering, so, and it's automatic, he will give him the number, so you don't have to care about the number here. This one is very important too, which is part ID. Each element have been created in LS Dyna, even its beam, shell, solid, whatever, have a part, is associated for this type of the element itself. So you can define the number or the part of the beam, or you can just let the LS Dyna start to give it a special part or a new part ID. Okay, now I'm going here to tell he asked me how do you want to create the beam element. So I will tell him that I want to make a beam element by, you have several choices here. So you have make a beam element by edge, make a beam element by curve, by node drag, by node span, by shell diagonal. In our case we are making it by a curve. Why especially a curve? If we close this window and go back again and stand in this command, you will find that it's curve, and that's what we have created here. So this geometry is a curve one. So we go here for element generation again and tell him we want to create a beam element using a curve. And after making curve, he asks you a very important question: what is your third node? Okay, for any finite element program, the beam element should have a local axis. This local axis, for example, we started our coordinate from this node till to this node. So we have an axe moving this-ward, and we have to define another two axes, which will be one in the vertical direction and one in the horizontal direction. To define these axes, we have to define a third node which refers for the vertical axis. To do that, we will click here, and to have a better clarification for this, if we have a view, see this PDF, here is our beam, this is the beam, and here is the axes that have been created in this direction, and this is the third node which will define the direction of the vertical axe, and corresponding to this axe we will define the horizontal axe, or the horizontal axe will be defined. So again, here in LS Dyna we want to define the third node location which will define the vertical axe. So I will tell him I want to define the third node location. Okay, the third node location, actually he asked me about the direction of the third node location. So I will tell him that the third node will be here at this point, above this point, with about z equal to 1 meter. So I go here, tell him that x equal to 0, y equal to 0, and z equal to 1. So he will create a third node located in this point, and will refer the axis of this beam to this point. Okay, now after doing that, I will pick the beam, and he asked me if you want this curve you want to create a beam from this curve, or by dividing this curve to a specific number of elements. I will want to divide this beam to 20 elements. You can specify any number of divisions you want. I will click create. Here is the beam is divided to 20 elements, and if you can see here, as we say, that he created the third axis in the direction that we describe in here, and accept. This way I have created the beam element from the geometry. After doing that, we have to start define the material, the section properties, and the loading, the boundary condition. But before starting in this, we want first to delete the geometry that we have drawn previously. It's not necessary to remove it, but you don't need it right now. So to do this, if you observe, you will find a list in the left side of the LS Dyna. This list contains every element, every part you draw here in the LS Dyna will be contained in here. So for example, I have two type of element. I have the shape group, which is the geometry, the line that I draw in the first, and I have the finite element part, which is contain the beam element that I have created. So for example, if I told him that to hide this, he will remove the beam element. You may not observe it well, but here it's visible. If I click this, he will remove the beam element from the view. So actually I don't want to remove it from the view, I want to delete it totally from the model. So I will stand here for the shape group, right click, and told him delete. He want to confirm the deletion. I tell him yes. So now the model has only the beam element, and now we want to start the definition for the beam element. So to define the materials, the boundary conditions, and every other things, we will use some tabs called the keyword manager. This is the main thing that we will start to define the whole things in it for the beam. So I'm going here in this tab, which is model and part tab, and here in keyword manager you will find that this is the keyword manager. Okay, you have only 3 lists here, element, node, parts. Actually these lists is for the current model, and you will find that these lists is for this model. If I told him show me all the lists, you will have all the lists that exist in here, and the blue one is having something defined for this model right now. So to start our definition, we want first to define the material. So I'm going down in matte material, and as you see here, you have different type of materials, lots of materials. I'm going to define an elastic material, and I will name my material as a concrete. And now here's the first step is the material ID. You don't have to care about this because LS Dyna will give it a number automatically. Now here is the mass density, the elastic modulus, and the Poisson's ratio. Okay, for these tabs we have to know what units we are using in our problem. And in LS Dyna there is a specific units you have to choose before you start your model. These units will be attached in the PDF that it will be attached with the video. I will show it to you here. Okay, here is a set of units for each type. For example, in our case we are using the first one. We are going to use the mass in kilogram, length is in meter, time in second, force in Newton, stresses in Pascal, and energy in Joule. If you choose any type of, or you want to change any type of your units, for example you want to use centimeter and mass with kilogram, then you have to use the remaining definition for the unit, and you have several here. This PDF will be attached with the remaining PDFs and with the video too. So in our case here we are using kilogram for the mass evaluation, meter for lengths, second for time, Newton for forces, Pascal for stresses, and for energy we are going to use Joule. Okay, let's go here for our case. For concrete, if we are using kilogram and meter cube, we have 2500 kilogram per meter cube. For elastic modulus is 2 to the power of 10 Pascal, Newton per meter square, and Poisson's ratio for concrete is 0.2. Okay, this is the definition for the material. After defining the whole things for the material, you can click accept. Then you will find, as I told you, will give the material an ID automatically and give its name and put it here in the list. If you want to add, for example, a new material, steel for example, you will tell him add. Then you will find a new ID for the material have been added here. I will name it steel. And for the ratios, the mass density will be 7850, and for the elastic modulus is 2 to the power of 11, and the Poisson's ratio is 0.3. Actually we are not going to use the steel in our problem, but it's just to show how can we define another material. Except you will add the steel material here. Okay, now after defining the material, we are going to define the section for the beam. So I'm going to search for the section list. You will find here section list. Expand the list. You will find several definitions for section, solid, shell, many others. I'm going to use beam section, and here for beam section I will name it beam 0.2 times 0.6. Okay, first the section ID. The LS Dyna will start to give it a definition itself like the material ID. Here is the very important part, the element formulation. Okay, for different cases we are going to use different element formulation, and for different type of element formulation you can use this definition and search in the internet to know what is this definition means for. In our case we are going to make a simple beam element, so we can use any type of equation 1 or equation 2 or equation 4. All of them give us the same result. For example, if you are making a truss element, you can find that equation 3 that will define only an axial forces for your beam element. But in our case we want to make a simple beam element, so we can use 1, 2 or 4. Actually the most accurate one in our results will be equation 4, which has a full cross-section integration. So I'm going to here use an element formation number 4. Now we are going here to define the thickness of the beam element. So we have TS1, TS2, TT1, TT2. To know what are these symbols refers to, we can see this figure. When we create a beam element in LS Dyna, you will find that this is the local axe, the axe created from node 1 to node 2, and here is the local axis of the beam. Is the horizontal axis T, the vertical axis is S. So the first length here is TS1, and the second length here, the vertical length, will be TS2, which is the thickness in the S direction at node 1 and node 2. Also here it will be TT1, the thickness of the beam at the T direction in the first node, and this will be TT2, the thickness of the beam at node 2. So here in our case, TT1 and TT2 will be 0.2, TS1 and TS2 will be 0.6. So here TS1 0.6, TS2 0.6, TT1 0.2, TT2 0.2. Except here we define our beam section. Done. Now after defining the beam section and material, we want to assign this section and material for this beam. And this beam, as we said, it have been created and have been set in a specific part. Every beam or every element you create in LS Dyna have a specific part ID. So to assign the properties for the beam, you are going to open the part list and pick your part, and then assign the material and the section for it. So I'm going here in the part. You will find that there is part and there is one definition in the part. If I open it, you will find that this definition is referred to our beam. So I'm going to give it a name here, beam. Here you find that section ID, there is nothing, there is 0. So if you click on this tab, it will open the list of the section definitions. So I'm going to pick the beam 0.2.6. So this is my section definition. And for the material definition, I'm going to open here. I have concrete and have a steel. I will pick the steel, the concrete one, sorry. So this is the definition for the material and for the section. I click accept. He will find that he changed the name, and he will keep these changes in the material and section. After defining the material and section, we want to define the boundary condition, the supports. We want to define a hinged support at this end and a roller support at this end, as shown here in the example. So to do that, we are going up in the boundary and we are scrolling down in the boundary list till we reach as SPC node. SPC is referred for a special point constraint node. Okay, this will be assigned for a node. If you have, there is some different options you can use in here. So I'm going here. You will find the ID as for the material ID, section ID. This one will be set automatically by the LS Dyna. Here in the title, I'm going to give it a hinged support. And here, very important point, that there is a node ID. He wants you to pick the node ID or the node number that you want to put the hinged. This one, and you will also have to define the node number that you want to put a roller support for it. So we don't have it here, or you couldn't know the node number. If you click here, you'll find several type of node or several numbers of nodes, so you can't know which node it is. To know the node number, we are going to close these tabs. Done. And here in element tools, you will find the first tool is called identify. This one helps you to know the part ID number, the part ID name, the element number, the element name, the node number, and so on. So I'm picking this, and here you have, he said, what do you want to identify? So then I want to identify a node, and then here is the selection set options. You can just identify the node by picking it. For example, click in here, then this is node number 1 that we want to assign a hinge, and click in here. So this is node number 4 that we want to assign the roller support. You can choose different options for the selection. For example, an area. So instead of picking, you can make an area here. As you see, this is the third node definition. He created a third node for each element. If I make a window here, you will find that for each beam element there is a third node assigned in here. Okay, let's clear it. I will clear node and then pick, and I want to pick this node, and I want to pick this node only. Okay, so I want to assign the hinge support for 0.1 and the roller support for 0.40. So we are going to close this, open the keyword manager again, go to the SPC node, and in SPC node I told him that I want to add a hinge support. The hinge support will be at, I can write down 0.1 directly without picking it or choosing here node 1. You can do both of them. And here he asks you about the degree of freedom that you want to restrain. In our case, we want to restrain the X direction and Z direction. Accept these changes. Now I want to add a new definition. So I will click add and type here a roller support and pick the node ID or type 40 for our case, and for this one I'm going to restrain Z direction only. Accept the modification. Here we have the two supports. For example, you don't remember the definition, you want to show the support definition. So we have an option here in LS Dyna that can you pick the first support and tell him draw. So you will find that here is SPC1, and then you can pick the other support and tell him draw. Then he will show you SPC40 for node number 40. You want to click done. If you finish, you have to first click none. You don't want to show anything, so he will remove all the drawings and then done and done. Okay, this way we define the supports, and finally we want to define the load. And to know the load, we have to know the node number, or first we are going to the node list. So we go scroll here till we reach the load list. Here is the load list. Open it. You will find different type of loads. For example, this is a gravity body part. You'll find this one define the gravity force. Also you'll find part gravity. This is define the gravity loading for the parts. We are going to scroll till we reach a node point. We are going to put a node load on a point. If I open it, here again he asks you about the node ID. The node ID that you want to put the load on it. So we have to know the node ID for the point where we want to put the load. So we are going to close this one again, and this way we have a problem that we don't know if we use identify as before. For example, I have to gamble where it is, so I can pick this node or this node. You don't know, so we have to know to measure the distance between this node and this node to ensure that point 20 or 21 or 22 is in the middle of the beam. To do that, we have a measure tool here. We are going to use it. So I'm picking it up, and I'm going to pick the 0.40 to 0.22. The distance is 2.25. It's not the middle node. Clear. 0.40 to point. Sorry, I pick it up again. So 0.20 is the one in the middle, because the distance is 2.5 and the whole beam distance is 5 meters. So 0.20 is the one in the middle. So I'm sure now that 0.20 is the one that I want to put the load on it. So I'm going here for the keyword manager, open node point, and here type 20 for the node ID. For the degree of freedom, if we stop in here, you'll find that for equation 1 is you are going to put the load in x direction, 2 y direction, 3 z direction, and so on for the others. So we want to put the load in z direction, so it's number 3. And here we have to define something called load curve ID. For LS Dyna, because it works in dynamic domain, so we have to define the time force relationship. What is the relationship between the time and the force? And also, after a while, some steps, we are going to define a termination time. What time will spend to run this simulation. So first we are going to define the load time relationship. To do that, we have to define a curve, describe this relationship, and to do that we are going to define a curve. So to do that, I'm going to press in this button. He told you that you don't have any curve. Do you want to define one? I will tell him yes, I'm going to define one. Then he asks you how are you going to define this one, using a keyword manager, that this is the manager, or using something called new entity. We are going to describe it later in our videos. So I told him I want to define it, use a keyword manager. When you do that, you will open the keyword manager, but for the curves only. Define curves only. It will not open any other tabs. So I'm going to pick up the curve. In the curve, I'm going to call it load curve. And here is the load curve ID. You don't have to care about it. The LS Dyna will give it a number. And here is the relationship. This is considered the time. A1 is the time, and Q1 is the value of the load. So I'm going to describe a load that starts from 0 till 1, increasing step by step. So at 0 the load is equal to 0, then at 1 second the load equal 1 unit, and at, for example, 2 seconds the load equal also 1 unit. If I click accept, he will tell you that you make some modification in the defined curve. Do you want to save these modifications? Tell him save. Then the load curve definition have been put in here. To ensure that the curve is as what we want, I'm going to click in here again and tell him I want to read this load curve. He opened this tab for me. I will tell him plot the curve. Here is the curve definition. So the load will start from 0, then increase gradually to reach unit value at 1 second, and then stay stable till it reach 2 seconds. Okay, I'm going to close it. Close it. Close it. Now for the value of the curve. Actually, the load value as shown in the example is not unit. Here we have a load value equal to 10,000 Newton in the minus z direction. So to define this load in here, we can do it two ways. Here in the load curve, instead of put the value of the load here 1, we can put it 10,000, or the other one, and this is preferred, to put the value here in the scale factor. So if you want to change the value, you don't have to change the curve every time. You also only have to change the value of the scale factor. So here I'm going to put the value of the scale factor minus 10,000, and it's minus, so it will be in the minus z direction. And I will tell him accept this load. So if, for example, you want to draw this load in the drawing, so we can click draw, you will have the load value in the z direction. It's minus 10,000. Okay, now we define the load. I click done. Okay, now our model is ready to be run, but before we run the model, we need, as we say, that LS Dyna is working in the dynamic domain. See, he need the time of termination for this run, how many seconds this run will spend to finish. So to specify this, we are going, let me close this tab, to going up in the control list, and in the control list, if we scroll down, you will find termination time. So I'm told him that I want this model to spend 1 second, which will be at the peak point of the loading, and accept. Done. Save the changes in the termination. After doing that, the final step, that LS Dyna will split this 1 second into some steps. So he will ask you how many steps do you want to divide this 1 second. You want to divide it to 1000 step, 100 step. How do you want your output to be plotted? Okay, to control this, we are going to database list, and this control the output type. You can plot it as a text file using ASCII option, and we are going to describe these in later videos. You can or choose any type of output. The most common output that we are using is the D3 plot, binary D3 plot. So I'm going here, and I told him plot an output for each 0.01 second, so I will have 100 output results, or 100 step for each result. I click accept. Done. This way your model is ready to be run. Then I'm going to open the LS Dyna program manager to run this model. First I have to save this file, so I'm going to file, save as keyword file, and here, before skipping this point, we have two major options or two major file extension. The keyword file will be the file containing the pre-processing, that containing the data, the definition, the material, and after making the run, we're going to open the binary D3 plot file, which containing the output. So here I'm going to file, save as a keyword file, and I'm going to put it here. So this is the file. I can save it. Now to run this file, I'm going to open the property manager, the program manager, and click and run a new keyword file. Here you ask you about the input file. I'm going to pick up the file that I have defined, just define it. So it was in here. Here's our file, and then click run. It will run the model for you. It will not spend too much time. It's done. Now we want to open the file, so I'm going to open the LS pre-post again and click file, new model. It will tell you you want to upload this. Sorry, yes. Okay, here's our pre-post. I'm going to file, open, and open a binary plot file. You'll find that this is our example, and here we have the D3 output. This is the D3 plot. Okay, the D3 plot is the major output that containing the all D3 plot outputs. D3 plot 01, D3 plot 02 is the file that containing the steps, or the each output for each step. This one is the collection for all the D3 plots. So if you have a very big run, you will have D3 plot 01, 2, 3, 4 till 100 maybe, and D3 plot you have to open it to contain all the runs. So I'm going to open this. Here is our model. If I click play, you can observe some deflection in the beam, but actually it's not very big enough. So how can we increase the displacement of the deflection? So to do that, we here, because we are in the post-processing, you will find that it's already in the post-processing mode. So I'm going here in the settings, displacement scale factor, make it for example 1000, apply. Here we can observe the deflection much better. So our models works well. Thank you. Okay, now we want to judge the output of the beam. To do that, we are going to the fringe output, and I want, this is a beam element, so I want to view the moment value. So I'm going to beam tab, and I want to view a moment. But we have two types of moment. We have S moment and T moment. In our case, we have to view the two T moment resultant. To know why specifically we choose this one, we are going to open this PDF. Okay, according to the right hand rule, this is the moment in the around the T axis, and this is the moment around the S axis. So we are concerning about this moment, which is the major moment, or around the major axis. This is the most important moment that we want to show it. It's in the Z direction. So here we are going to show MT, and to test the output we are going to view MT at its maximum value. So the value of the moment, as you can see here from the sets, it's the maximum value. Here it's 1.246 e to the times 10 to the times of 4, and you can observe it here too. It's 12459.9 Newton meter. To ensure this moment is it right or not, we use to calculate the moment manually for a simple beam case. So for a simple beam case, the moment is PL over 4. The P is 10,000, L is 5 over 4, so the moment is 12500 Newton millimeter, and the actual moment here is 12459.9 meter. So it's almost the same. The difference between both of them is because of the change in the number of the elements. So if you increase the number of the elements, you may have a better output. This way you define a simple beam, have a concentrated load in the middle. Later we are going to describe some other complicated problems containing a moving load over a simple beam. Thank you.